let's talk about simple notation, right? Simple notation. And this is something that chemists use a lot when solving problems, and it'll make y'all's life a lot easier as well. So, the first thing is if you see something called an HA, that stands for a weak acid. And then if you see an A minus, that is a charged weak base. And H plus is a strong acid. And OH minus is a strong base. And lastly, or not lastly, we have BH plus, which is a weak acid, and a B, which is a weak base. So looking at this right here, let's talk a little bit. It's not something that I expect y'all to be familiar with right now, but something about conjugates. So when we're talking about weak acids and weak bases, these two right here are conjugates of each other because we're losing a proton to create this weak base. And then right here, we're losing this proton to create a weak base right here. And the difference right here, and we'll look in later videos on how to actually use these to solve acid-base problems, is this right here is charged, and this right here is charged as well. So this is a weak acid that's kind of neutral, usually has an H in front of it, and this is going to be charged. And that's how you kind of differentiate. So let's talk about acids that you might encounter and how to categorize them, because that's the first step to actually solving these acid-base problems. So, okay, let's look at a kind of simple one. So let's look at the strong acids and strong bases. Strong acids and strong bases. So these are acids that you should be familiar with. You usually have 7 or 8 strong acids, and just knowing these off the bat can just make your life a lot simpler when it comes to naming these. So the first one we can look at is HBr, is a strong acid. We have HNO3, nitric acid, is a strong acid. We have hydrochloric acid, hydroiodic acid, so it's important to know these names as well. HClO3, which is chloric acid, HClO4, which is perchloric acid, H2SO4, the only polyprotic acid that is a strong acid, sulfuric acid, and then HiO4, which is periodic acid. So you won't really see the last one as often, but it's good to have it in mind. Now, strong bases are really easy if you know your spectators. So when it comes to strong bases, we can categorize these as well. So we have LiOH, so lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide. Notice this is because calcium has a +2 charge, strontium hydroxide, and barium hydroxide. So now that we have these out of the way, you're going to have to be able to identify spectators. So something like an iodine or a strontium or a calcium. These are spectators, and when you put something like KOH into water, you're going to automatically break it apart into K plus spectator ions and then strong bases, also known as OHs right here. So let's talk about some simple examples. So if I give you something like hydrochloric acid, this one, we're going to label it as a strong acid, first of all, and it is an H+. So we want to make sure we can label it in this notation right here, because it's going to make your life a lot easier when it comes to solving these problems. So let's look at something a little bit more complicated. Potassium malonate. Now, notice this is an 8 ending, so usually when we have these 8 endings, we can say, okay, this is probably a weak base, because this just means that you have removed already this hydrogen ion, so it's some kind of conjugate weak base. All right, and if you see an ic ending with it, unless you have like nitric acid, you can usually say it's a weak acid, but that's not a hard and fast rule. So potassium malonate. So potassium itself is a spectator ion. So as soon as it comes into water, it just falls off and doesn't react. And so once we get rid of this positive potassium spectator, we have a weak base of some sort, and it's also charged. Because it's a charged weak base, I can say that it's labeled as an A-. Now let's look at NH4Cl. This Cl is a spectator as well, so it falls off, and so when you get rid of that negative charge, you have a NH4 positive, and this is an example that y'all should know. It's ammonium, and it is a weak acid. And because it's charged, we can go back and see that it matches this description right here, where it's BH plus right here, and say that this is a BH plus. All right, let's do something like this. HCOOH. If this is what you're given, let's say you're titrating with, and you start out with this. This, we know it's not a strong acid, okay? So, and it ends in H right here. This COOH tells you that it's a carboxylic acid, and that tells you that it's a weak acid. All right, because it's a weak acid, we can say, and it's not charged, we can say this is an HA. All right? Tartaric acid. All right, tartaric acid, it ends with ic. It's not strong, so we can kind of cross that off. We can say it is a weak acid. All right, so we can say this is a weak acid and label it as NHA as well. All right, y'all see how we're getting this? This is not charged, which is why we chose HA instead of BH plus to label it. All right, what about something like lithium hydroxide? All right, lithium hydroxide falls into the strong base category. We can see it up there. So lithium is a spectator, meaning this hydroxide would have a negative charge. So you can say it's an OH minus, and it's a strong base. All right, let's do something a little bit more complicated. CH3, 2NH. All right, so this kind of tells you that it's some sort of amine right here, and anything that ends with NH4 plus is different because it's a weak acid. We have ammonium, but anything that usually ends in NH with this carbon group right here would be some sort of amine. And so when we're looking at some sort of amine, it's usually a weak base. And I know this seems like, oh, this is not intuitive yet for me. It's just going to come with practice. The more problems you do, the faster you get at recognizing these. And so because it's a weak base, we know it's not charged. As soon as we know it's not charged, we can say, all right, it's not charged, it's not an A minus, so it has to be a B. All right, same thing for something like if you're given dimethylamine, instead of having it written out, right? This is dimethylamine, and even if you don't know enough organic chemistry to be able to draw this out, you don't need to draw it out, you don't need to know the chemical formula. It's some sort of amine, weak base, and there is no spectator to cross off, so we can't say it's charged, and so we can label this as B. All right, let's do phosphoric acid. All right, phosphoric acid, you're going to learn is a triprotic acid, and it ends with an ic. There's no spectator to cross off, so we can say it's a weak acid. and it's NHA because it's not charged. And we know weak acids are HAs right here. And this is actually a triprotic. This is actually a triprotic acid, so we can say this is actually H3A. But we'll get there eventually. All right, what about H3PO4? All right, we know it's not a strong acid. There's no spectators to cross off, so it's not charged. So it has to be some sort of weak acid. We have this H right in front of it, so we can say that this is an HA and it's not charged. All right, so the next one, let's look at something a little more complicated, BH3. BH3 is, we know it's not charged, so, and it's not a BH+, and it's not charged, so, but we can see that because of these H's, this is something that you have to memorize. It's a weak acid, and it's specifically a Lewis acid. And this is just one of those weird examples. I just wanted to throw that in there so that you guys were comfortable with it. All right, so let's look at something a little more complicated. I'm writing ammonium acetate. Now, ammonium acetate, we can see that there are two kind of species in solution. And looking at these two species, we looked at ammonium before, and ammonium before was written as NH4+, and acetate was, we can see we have an 8, so it's some sort of weak base, and it's charged, and the chemical formula is CH3COO-. And so when we stick them together, we have this neutral NH4 CH3COO- COO compound, and when we stick into water, it immediately breaks up into these two molecules. So NH4+, we already said that it was a BH+, which is a charged weak acid. And all right, so looking at acetate, however, we can say that acetate the H has come off just like from when we looked at COOH was a weak acid. We removed that H, some kind of ion right here. So it's some sort of 8 ion situation going on. All right, so this obviously is a weak base of some sort of. It's charged, so we can say that it is an A-. All right, so let's move on and do one last one, sodium carbonate. So sodium is a spectator right off the bat, so it has a plus charge that it takes away with it. So we're left with one negative charge on carbonate. And so we can say that it is an 8 once again, so it's some sort of weak base, it's charged, and we can say that it is an A-, right? Because it's a charged weak base. All right, so you can see that these are important for y'all to be able to recognize when you come across these on acid-base problems. You're not going to be given the fact that it's HA or B, you're just going to be given tartaric acid or something like that, or phosphoric acid. And it makes it simpler to just do acid-base problems. So looking at this at the bottom, BH+ is a weak acid like we talked about. If you stick it into water, it breaks up into, or the H+ dissociates from the BH+, and we're left with B and an H3O+ or a hydronium. If we take a weak acid and stick it into water, we're left with an A- and an H3O+. And then if we take a charged weak base, that water acts as an acid and gives up that H+, or an H+, yeah. And you're left with HA, so weak acid, and an OH-, a strong base. And you can do the same thing with B, stick it into water, and you come out with BH+ and OH-. And then for the last one, if we take a strong base and a strong acid together, we're going to be left with neutral water. So it's equations like these.